Okay, so the puzzle I put up there to start off with is this one here. So you have $15 in $1 bill. So I thought I'd give you a visual representation just in case you didn't know what dollar bills look like. And the idea is that you've got 4 envelopes. And you want to put the dollar bills in the 4 envelopes so that you could still pay any dollar amount between $1 and $15. Okay. So where do we start?
You need one envelope with $1.
Great. So that's a great start. So you've got to be able to pay the $1 amount. So your first envelope. So let's draw our 4 envelopes. The first envelope has to have $1 in it. Okay? So we've taken care of paying the $1 amount. Okay, so where do we go with these puzzles? We always say you just kind of take the next step along the line. So what's the next dollar amount that I need to work out how to pay? $2. So what should I put in the second envelope? $2, right? Let's put $2 there. Now, I could have just put another envelope with $1 in it, but that seems a little kind of wasteful. And what do you notice? What dollar amounts can I pay with these 2 envelopes? 3 as well, right? 1, 2, and now add them together, you get 3. Okay? Well, let me do a table for you. 8, 4, 2, 1, and I'm going to pick a particular number. I'll do 13 to start off with. So how did I do 13? What was that?
8, 4, and 1.
8, 4, and 1. So there were no 2s. So 1, 1, 0, 1. Okay, so what is that? Binary. So this is exactly how binary coding works. It's 1s and 0s. And so the 1s and 0s refer to the powers of 2 in that decomposition. So 13 is 1, 8, 1, 4, no 2s, and 1, 1. So just to do another one, if we did, say, 15 is 1, 1, 1, 1. Okay, and so if you needed an extra row, what do you think the next column would be here? 1, 2, 4, 8. 16. So binary numbers are kind of opposite. They go from right to left rather than left to right. So you'd add another 16 here. So if it was 5 digits, you'd need a 16. Okay, so this is binary code, exactly how binary code works. Okay, so there is a joke, and I'll write the joke up here. Okay, so that's the joke. You can judge whether it's funny or not, but it's accurate. Okay, so we'll make a start with what we're gonna cover today. Okay, so the first thing we're gonna talk about is a little bit of a recap of what we did last time. So last time, remember, we talked about the maximum and the minimum of a function. And we defined that in a couple of ways. We talked about local maximum, local minimum, absolute maximum, absolute minimum. And the picture was something like this. You had a graph on a particular interval. Something like that. And you want to talk about a relative maximum, or in our case we use the term local maximum, and a local minimum. But then if we're talking about on this interval from A to B, then really the absolute minimum is here at A, and the absolute maximum is here at B. So what I'm going to do is I'm going to put up an example. This will be example 4.4.1. And the first bit is y is continuous necessary. And part B is y is differentiable necessary. Okay, so what I want you to do is I want you to get in pairs, and I want you to come up with some functions that satisfies everything else but doesn't satisfy the conclusion. So you want to come up with some function that f of a equals f of b but is not continuous, and so therefore there's no point in the middle with slope 0. Okay? And the same thing for differentiable. Okay? Does that make sense what I'm asking? So come up with a picture of something that's not continuous but does have f of a equals f of b and no point in the middle with slope 0. Does that make sense? At least give it a kind of a little thought, and then we'll come back together. So put yourself in pairs. Find yourself in a pair and try and draw something. Threes are fine if you're in threes. So you know, here a picture is plenty enough. Doesn't need to. You don't need to write out exactly what the function is, but a picture is good.
It'll be 0 at the bottom.
So that looks good for, but think about that's continuous, right?
Yeah, so you have to do the
So, but think about that might be a nice example down there.
Oh, the one that's not different.
Yeah, because it's that point right there is not differentiable, right?
Oh, so this one may well as continuous.
Yeah, that is continuous, but it's not differentiable because that you remember, differentiable, another word we used was smooth. And that's definitely not smooth at that point there, yeah. Sharp, yeah, that's a nice one.
So it has to go through both points.
Yeah, it has to, so basically imagine that you've got these 2 points fixed, but you're not continuous or not differentiable. And yeah, those look great. So that would look good for the differentiable, right? But that is continuous. So it's even, you think of an even kind of messier thing for the not continuous one. Think about those piecewise functions. Remember that the just kind of cut and paste ones. Those would work pretty easily. Okay, so let's come back together. Most of what I saw people working on looked great. So the first thing, so for not continuous, let's just remind ourselves what does continuous mean in a really general sense, not kind of down to epsilons and deltas, all that business. Yeah, so not being continuous means you don't pick up your pencil. So if I'm throwing away that consideration, if I say I don't care if it's continuous or not, then pick up your pencil, right? So I could do something really kind of messy, like go there and then go here. So piecewise defined function, right? That's kind of in general what we're talking about. We're talking about a piecewise defined function. And is there a point on that graph with slope 0? No. Okay. Differentiable. So I spoke to a lot of people. We said smooth is what you want to have in mind. If something's differentiable, it's smooth. Everything's kind of nice and smooth. So do something sharp. So do something a little bit sharp like that. And you want to have that absolute value function in your mind. Is there a point on that with slope 0? No. Kind of if I smoothed this out, if I kind of made this smooth, that would be where I'd want it to be slope 0, but it's not, it's sharp. Okay? So these two conditions, continuous and differentiable, are absolutely necessary. Are absolutely necessary. In between. Okay? Okay, so what we're going to do to finish off this hour is we're going to do a little bit of a review of what we've done here with the mean value theorem and Rolle's theorem, and we're going to do a Kahoot quiz. So if you want to grab out your phones, we'll do a quick Kahoot quiz. to just make sure we've got all of these details tied in. So we've said that these are existence theorems, and there are some conditions that we really need to make sure are applied. So let's make sure we understand the conditions to Rawls' theorem and the mean value theorem. So these are just 4 questions just to make sure you fully kind of got to grips with mean value theorem and Rawls' theorem. Okay, so this was a little technical. So remember how I wrote those intervals down. One was closed, one was open. Seems kind of a technicality, but it is kind of important. So here we go. So let's make sure we have this right. It was continuous on the closed interval, continuous on the whole way, and differentiable just on the middle bit. So it didn't really matter. So an example here, it's got to be continuous on the closed thing and differentiable on the open interval, because differentiable doesn't take into account the endpoints. It doesn't even make sense to talk about differentiability at the endpoints. Okay, so it was this last one right here. Okay, so let's do the next one. Okay, so there's a particular function, and it's asking whether it applies, the mean value applies between -2 and 2. Okay, so great, everyone got that right. So no, it doesn't apply because it's not differentiable at 0, and that's kind of make sure we work that through. So it was between -2 and 2. Absolute value of -2 is 2. Absolute value of 2 is 2. So in fact, that's really kind of Rawls' theorem, right? It says there should be somewhere in the middle where the slope is 0. But the problem with the absolute value function is it's not differentiable at that kind of sharp point. Okay, so it's not differentiable right here at this kind of really sharp point there. It's not differentiable.